back to the question. So last time we discussed the capacitors, and I kind of gave these hypothetical situations where we charge up the capacitor, disconnect the source, the supply, and then we play around with either the plate area or the plate separation. And the idea there was to get some sort of conceptualization about how the physical dimensions of the capacitor affect the equipotential lines between the plates. Then I said, hey, go ahead, think about this as you go to lunch, think about it as you're eating, or when you're trying to relax or going on a walk and it pops into your head. Because the best thinking always happens when you're not actually trying to think. Right? And I said, well, let's do the opposite situation. Charge constant and thinking about the electric potentials, let's hold the potential difference between the plates constant and think about what happens with the charges. So here we go. I said, okay, let's take a capacitor and connect it to a battery. Now, I will say it here, I will say it again on Monday when we get to batteries. Batteries, the sole purpose is to provide a constant electric potential. And I should say a constant difference in electric potential. That is what a battery does. Duracell, Energizer, Rayovac, or some other brand. Okay? The whole point of a battery is to maintain a constant potential difference for as long as possible. Because it's not an infinite supply. So I hooked the capacitor up to a battery, and the battery is keeping the plates of the capacitor at a constant difference in electric potential. Okay. Now, while the battery is attached, so that's the difference, right? The difference earlier was put the charge on, unhook the battery, then play. Here, I want to keep the battery on, and we're going to play. Question. As I increase the distance between the plates, what can you tell me about the amount of charge on those plates? So the battery is attached, I take the plates of the capacitor and stretch them apart. What happens to the charge on the plates? Go ahead, talk to your neighbor, get an idea. What happens? Charge goes up, charge goes down, charge stays the same. Good review, good review.
Yeah.
Where does that go?
What is like the question said that the
yeah, so when you're doing on Wednesday, there's no place for the charge to go, right? I unhook the capacitor from everything so the charge is tracked on the plates. Okay. So then as you move the plates, there's stuff that has the electric field or potential. Here, I'm keeping the electric potential constant, I'm keeping the capacitor. So as I stretch the plates, there's places for the charge line move. So the question is, does extra charge go on the plates, or does extra charge go on the plates? It's a little less obvious. The reason I start off with the other one is because it's a little easier to conceptualize. This one is a little harder. It's the same ideas, it's just kind of working through it. I don't know, you want me to work through it? You got an idea? I mean, should I go through it?
Yeah.
Yeah, okay, I was making sure. about it. And the reason the reason I start off with the stuff on Wednesday is because that was a little easier to think about the charge being tracked and get the equipotentials. And here, the equipotentials stay the same, and then the charges change. It's a little harder to kind of think about. So here, yeah, I think I actually have here. Okay, wake up. There we go. So let's, I'm going to start off with, maybe I'll start off with something if it lets me go. Go. There we go. So the first thing I'm going to write down here, I put in, excuse me, I put in two things here. Number one, I've substituted in the expression for the parallel plate capacitor. Okay, we came up with this expression on Wednesday. Epsilon naught area divided by D gives me the capacitance. And similarly, I put in, theoretically, this should be an equivalent sign, a triple equal sign, but I've fallen to my physics trap where I just put an equal sign in. I put in the definition of capacitance. So for a parallel plate capacitor, here's the expression relating the geometric quantities. And then right here, I put in the definition of capacitance. And next thing, oh yeah, go.
Sorry.
Yeah.
I don't understand how the electric potential can stay the same and the distance.
Yeah. This goes into the next question, actually, if I may. Well, I guess the thing I was going to ask is, which quantities in this expression stays the same? Constant. So I hook a battery up to the capacitor, which means the difference in electric potential across the capacitor plates stays the same. That's the purpose of the battery, is to hold at a constant difference in electric potential. Nay, maybe.
Wait, so the battery keeps the electric potential the same?
Yeah, exactly. So let me draw a picture here. Let's say here's my capacitor, the two plates on my capacitor. And for lack of a better drawing right now, I will just put in a battery. And I guess I've set the cart before the horse here, but this would be the positive terminal, this would be the negative. What we mean by that is the high potential side and the low potential side. Okay. So what happens, I will run a wire from the high potential side and it will connect to the capacitor plate. I will run a wire from the bottom side to the low potential side of the battery. And because I've connected it using conductors, charge will move around until the potential difference across the battery equals the potential difference across the capacitor. But that's what I mean by we hook up the battery. It will maintain a constant difference of electric potential between the high terminal and the low terminal. Incidentally, if you check it like a AAA battery or a AA or a C or a D, if you look on the side, it will tell you 1.5 volts. That battery is designed to provide a constant difference of 1.5 volts between the positive terminal and the negative terminal. Of course, you know the fire alarm batteries, right? The little boxy ones. We call those nine volts, right? You say, oh shoot, my fire alarm's going off, I have to replace the 9-volt battery. Yay, nay, you know the little boxy ones where you say, oh, is it still good, and what do you do? No? You're not a fan? You don't lick the terminals of the batteries? I mean, clean it first, but if you want to know if a 9-volt battery is good, the nice thing is that the two terminals are on the top, so you can lick it. That provides a conductive path. And if you feel a little tingle in your tongue, then it's still good. You haven't tried this? Make sure to clean the terminals, of course, but yeah, you can just lick it real. Is the battery good? You just lick the terminals, and if you get a little tingle through your tongue, then it's still good. It's harder to do with a double A or a triple A, right? Because the terminals are on the opposite side, so you can't, right? Like, no, that's not gonna work, okay? But the 9-volt batteries is pretty easy. Oh yeah, piece of cake. I mean, make sure that you're the only person to have licked it. That's probably the big thing, right? Well, okay, so this is in the day and age where we don't worry about coronavirus, right? Like, I mean, like, you just, yeah, it's not bad. It's not like your tongue goes numb or anything. So, yeah. Okay, so but this is the purpose of a battery, is to maintain a constant difference in electric potential, which means the upper and lower plates have a constant difference. Remember, there's no way, there's no connection here. Right, there's no lines or anything. So this one's at one potential, this one's at a different potential. What else is constant? What other things stay constant? The area? Okay, so the area. What else stays constant? The constant, epsilon naught. Let's put all the constants on one side. So the area is constant, epsilon naught is constant, the delta V is constant. So I'll just say the constant, grouping all these constants together, epsilon naught, the area, and delta V, and then I'll put Q and D on the other side. And then hopefully you see now, if I increase D, if I make D larger, if I separate the plates more, what has to happen to the charge on the plates? It decreases, right? Inversely proportional. As D increases, the charge has to move off of the capacitor plates. Of course, if I go the other way, if I make D smaller, what happens? It increases. Charge has to dump back onto the plate. Here's the other piece. A battery provides a constant difference in electric potential. A battery does not necessarily have to supply a constant current. Right? Batteries provide constant differences in electric potential, not constant currents. Or maybe I say a battery is not designed to furnish a constant current. It is designed to furnish a constant change in electric potential. So you can literally take a capacitor, hook it up to a battery, do this, and you are moving charges. You could create a current in the wires. You do this, current flows on, charges flow onto the plates. You do this, the charges flow back off. This, on, off, et cetera, et cetera. I always find that interesting because you can do some sort of mechanical motion to force electrons to move or charges to move. I just find that interesting for some reason. Or you could literally you could take capacitor plates, hook it up to a battery and do this, and you're physically forcing electrons to move through mechanical motion. I find it fun to think about, at least, but that's just me. Yeah. So yeah. Oh, yeah. Excuse me. Let me get my drawing out of the way here. There you go. Yeah. So you can think of, as you move them further apart, you drive charges back into the battery. Right? The charge has to decrease. That forces the charge to go back into the battery. That animation again. That took so long. There you go. Of course, then you say, well, great, but the wire's not connected. Okay. I tried. How about the area? Let's say instead of increasing the distance between the plates, what happens if I increase the area of the plates? What happens? What happens to the charge? Okay. keep the battery connected, but I make the area of the plate larger. The charge increases, right? You could write, and I'm sure I have this on another slide, but I've got it here. So you could write constant equals the charge divided by the area. As I stretch the area of the plates, keeping it connected to the battery, essentially there's more places for me to pack charge, so more charge moves onto the plates. If I make the area bigger, more charge can be packed onto the plates. If I make it smaller, less charge can get packed onto the plates. Yay.
Can you explain that one more time? Because I feel like if you're increasing the distance, wouldn't you also technically be increasing the area? Like, I don't know, it just like doesn't make sense why you're getting a different result, but basically doing the same thing.
Yeah. So when I increase the distance, or excuse me, when I'm saying the word area, I don't mean the area between the two plates.
Okay.
I mean the physical size of the plates themselves.
Oh. Okay.
Does that help, or does that help clarify? Yeah, okay. So I'm not talking about the area between the two plates, I'm talking about the physical size of the plate itself. And so yes, the physical plate is larger, there's more, if you will, locations to put charge. And so the charge goes up. I think that's all I have to say about that. Yeah. Oh, okay. Here's oh shoot, I forgot about that. So we've already what was I going for? So there is a convenient way. Yeah, I'm all off. Okay, so I thought that there was a different slide and there's not. Okay. So we've got an idea about, okay, if we keep the source connected and stretch the area, we get more charge. If we shrink the area, we get less charge, and same thing with the distances here. So here's another question for you, because usually when you see a circuit, you're gonna start having to figure out how to analyze it. And a circuit could have multiple capacitors. So, so there's some really easy rules for combining capacitors. This arrangement is called you have two parallel plate capacitors in parallel. So I realize now I need to talk series, parallel. Okay, so I'll throw it out there. It's always hard for me to come up with a great analogy. The first thing I think of is the World Series. Right, baseball, here. So you go to the World Series, you play theoretically it's a best of 7. And so the thing I always think about is, what do you need to do in order to get to game number 7 in the World Series? Or maybe I should say, what do you have to do before game 2 in the World Series is played? You have to play game 1. And to get to game 3, you have to play games 1 and 2. Right? The reason we call it a series is because you don't play all 7 games at the same time, simultaneously. What you have to do one by one by one. You have to go sequentially. To get to game 5, you have to play game 4, 3, 2, and 1. Okay? The same thing will happen with, say, something like capacitors. If I have 2 capacitors in series, what that means is charge has to flow through one capacitor before it can get to the second capacitor. In fact, maybe I should take byline. Let me put in an extra blank slide and let's go this route for a second. So I'm realizing there's a gap in my presentation here. Yeah. Nobody needs to, no, I swear I just put it in. There it is. There we go. Okay, let's do it this way. So let's say for a second, I've got a parallel plate capacitor. and we've discussed what it means to charge it. If I want to charge a parallel plate capacitor, I can take some positive charge, force it onto the upper plate, which becomes positively charged. Because of this excess positive charge, it forces positive charge off of the bottom plate, and so the bottom plate becomes negatively charged. I did a little animation, yada, yada, yada. Now let's pretend for a second that I have a second capacitor along this line. In other words, somewhere down here, I put a second capacitor. Good so far? This positive charge forced off of the bottom plate of the first capacitor gets dumped onto the top plate of the second capacitor. And of course, the bottom plate of the second capacitor sees the positive charge on the top plate, and that forces positive charge off the bottom plate, which carries on its merry way, and you end up with a negatively charged bottom plate. It's kind of like a cascading effect, right? You force it off the bottom plate, it goes to the top plate, force it off the bottom plate, yada, yada, yada. In other words, for charge to arrive at capacitor 2, it must first do something with capacitor 1. To get to capacitor 2, you have to go through capacitor 1. Say through, quote unquote. Put it entre guillemets, air quotes. So this is what we would refer to as a series arrangement. To get to 2, you must first travel, quote unquote, through 1. While I'm at it, I should ask this, just curious. The charge on the first capacitor, how does that compare to the charge on the second? Go ahead, talk to your neighbor. The charge on the first capacitor, let's say the top plate. The charge on the first capacitor, how does that compare to the charge on the second capacitor? Yeah, go ahead, talk to your neighbor, get an idea. Go. Yeah. Still have coffee. Yeah. What if you have a bigger eraser? If you're doing it right. Oh, so that makes me sad to see such a tiny little eraser. I don't know. Why? I don't know. We should get you a bigger eraser. I mean, how can you get onto that thing? Just like a piece. Yeah, you need like a bigger eraser. We'll fix that. Something. Oh, this? Yeah, this is, I kept losing my mask. And so my wife said, okay, I've had enough of this, and so.
I like to something really fun, like work break or something, got your ear.
Woohoo! Yeah, got a haircut.
Really helping.
Well, you should see the tattoo. I don't remember it at all. No, I don't have any tattoos. No.
I'm really excited.
Yeah.
Like first you're telling me watch the exercise, and I get tattoos.
I didn't. Yeah, that's how it came across. I realized it later.
One day I'm just waiting for you to put the ball.
What?
Waiting for you to put the ball one day.
You want me to? Not with your thing open. No, your water. Okay, now I'll throw it to you. There we go.
It's squishy.
Yeah, it's just a little dot ball. You got it? Well, you've got the ball, you've got an answer. Oh, yeah. Okay, now. Oh, I don't want the ball. Yeah, what do you got? All right, I said, how does the charge on the top capacitor compare to that on the bottom?
The one on the first one be greater.
Yeah, okay, so one option is the charge on the first capacitor is greater than that on the second. Okay? Yeah.
What if the same amount of charge from one have to go to two, so wouldn't the charge stay the same?
Yeah, okay, so now we've got it's the same. So now we've got two answers. Who are you voting off the island here?
Four.
I don't know, unless Corey wants to revise the statement.
Sticking with it.
You're sticking with it? I love it. Yeah, put your stake in. It's like not stand and deliver. That's the calculus movie. Far and Away. I think it's Far and Away. Tom Cruise, Nicole Kidman. It's about the Oklahoma land rush.
Sure.
Yeah, and there's this end scene. So the land rush in Oklahoma was essentially, in the movie, is essentially you just run out, you grab the stake off of the property that you want, you plant your flag. So there's like some climactic battle between Tom Cruise and somebody else because they're fighting over the same property. And I vaguely remember like Tom Cruise pushing the guy down and ripping the claim flag out of the ground and planting his flag in, so he's claimed the land. So I love it. You planted your flag. You said, nope. We're gonna push you off the island anyway. Everybody, oh.
So like, what's the purpose of like amplifiers that need those?
Ooh. Amplifiers, okay, you ready for this one? Beyond the scope of the course. Yeah, but you are right that we are going to move into what's called passive circuit elements. That's kind of the technical term. You don't need to worry about that either. What I mean but amplifiers are what are called active circuit elements. They require an external power supply in order to operate correctly. Okay. Capacitors are what we call a passive element. In other words, in order for it to work, does not require any external power supply. You can hook up a potential difference and it automatically works. Okay. Amplifiers require, it's a higher form, it's a beyond the scope of this course, but it's a more complicated electrical system. But I agree with you, if you're dealing with an amplifier, then one of the things that an amplifier does is provide a variable current or variable charge supply. Yeah, so the idea here is that any charge that leaves the first capacitor must get deposited on the second one. There's nowhere else for that charge to go. So if you force 10 coulombs of charge off of the first capacitor, that 10 coulombs of charge must be forced onto the second capacitor. Yay? Is that okay so far? Yeah.
What if you had a resistor between the two?
Oh, that's a good question. And we will have to, this is getting into what will be the next chapter. But I said, oh yeah, I hate Kirchhoff because he states the obvious. What you, if I may say, you were asking me something that deals with Kirchhoff's laws. And let's answer the question. If you put a resistor between the two capacitors, does that provide any place for the charge to leave the circuit? No. So what ends up happening is that even if there's a resistor between the two, resistors do not remove charge. They slow the charge down. I say slow the charge down. More specifically, since we're off on it, resistors remove energy from the circuit. It removes some of the kinetic energy of the electron, but it does not remove electrons themselves. The electrons stay there, it's that they slow down, which I guess is probably a good thing. So one example, just think of a light bulb as a resistor. The whole point of a light bulb is to slow electrons down to the point where the wire heats up. And if you get the wire, the tungsten wire in a light bulb hot enough, it starts emitting visible light. So you can think of a light bulb as a giant resistor, and the whole point is electrons are trying to move really quickly through the wire. The wire slows down the electrons, removes kinetic energy of the electrons. That manifests itself in heating up the wire itself. So that's a little bit further away, but we'll get there. But does that answer your question? Okay. And that's a common, I'll say also, please be aware, I'll say it now, I'll say it again when we start talking about resistors. Resistors do not remove current or charge. Resistors do not remove charge from the circuit. They remove energy from the circuit. The charge stays there. It's the energy, it removes the energy. Yeah. Okay, so capacitors, if I have a top capacitor and a bottom capacitor, the charge on those two capacitors are the same. There's nowhere else for the charge to go. Charge that leaves the first capacitor, it must be deposited onto the second one. Good so far? Now let's do a Gedanken experiment. One of the other things it's kind of glossed over. I say that I'm going to assume when I connect circuit elements like these capacitors, I've been drawing a wire, right? This is supposed to be a wire right here, connecting the two, giving a path for the electrons to follow from one location to the next. Okay? We will assume that all wires are perfect. What that means is that the electron can move freely through the wire without losing any energy. Okay. So sometimes you'll see the phrase a perfect wire. Okay. The electron travels from point A to point B without losing any energy. And again, no wire is perfect. Copper, a very good electrical conductor, still not perfect. If you make a copper wire long enough, say, I don't know, from Hanover College to Clifty Falls Power Plant, 5 miles long, you'll start getting some appreciable, energy removal, right? So we will assume a perfect wire here. The second thing I'll point out, perfect wires are free. I can make the perfect wire as long or as short as I want, and it doesn't change the behavior of the circuit. Is that okay? So I just want to say perfect wires don't affect the behavior of the circuit. Because it doesn't affect the behavior of the circuit, I can draw them as long or as short as I want. Okay. So I'm going to do a little thought experiment here. I'm going to take this perfect wire that connects those two capacitors, and I'm going to make it small, really small. In fact, I will make it so small that I have my first capacitor like this, and I'll do it in a different color just so that we have some contrast, green. Here's my second capacitor. I'll draw it just like this. Like that. There we go. In other words, I've shrunk that wire that connects the two all the way down. Is that okay? Yeah, the perfect wire between the two capacitors, I've just shrunk it down to essentially 0. So I want the bottom plate of the first capacitor to overlap with the top plate of the second one. So I just drew it visually in there. Good so far? So here's the question. When I put capacitors in series, does it increase the capacitance, the overall capacitance, or does it decrease the overall capacitance? So if I put 2 capacitors in series, do I increase the capacitance or decrease the capacitance of the entire circuit? And consent? Yeah.
Yeah.
Let's say,
Increase? Increase?
yeah. Actually, maybe I'll do it this way. So compared to capacitor 1. So let's say, sometimes this is called the equivalent capacitance. Okay, well, I can't spell equivalent over my shoulder. Equivalent capacitance. So the question is, how does C1 compare to the equivalent capacitance? Yeah. So is the equivalent capacitance greater? Is it less? Is it the same? So you said less or greater? Is that what you?
Wait, so what's the question?
Yeah, how does the equivalent capacitance, the two capacitors in series, compare to the capacitance of, say, just one of the capacitors?
Okay.
Mhm.
I don't think it would change at all, would it? Because, I mean, if you have the same charge on third and everything is literally the exact same, like the distance, it doesn't change between the first one and the second one.
Yeah. So,
Change.
yeah, and that's what I want you to compare. Yeah, I see what I want you to do is compare just this lone capacitor to, say, a combination of two capacitors. Yeah. So that's why I was trying to clarify here. You've kind of caught the right idea, though. Did the distance between the two plates increase or decrease, or stay the same?
So were those two, like, with, on the equivalence one,
Mhm.
the bottom, I guess, of the top plate and top of the second plate?
Yeah.
Would they basically be touching?
They basically be touching, yeah.
Would that cancel out and call the top plate and just kind of use the pass charge through it?
Yeah. Do you see, if I put the bottom plate of the first on the top plate of the second, that's essentially putting the same charge at the same location. One's positive, one's negative, so you can conceptualize that as them canceling out, if you will. In other words, physically, there's two plates there, but conceptually, you can ignore them completely. Yeah, I agree. I like that idea.
So then, if B would technically double, then what if the capacitance would be cut in half?
I've increased the distance between the capacitor plates. What happens to the capacitance? You said it decreases.
Yeah.
Yes, exactly. Right, so what happens if I increase the capacitor plates? Right, the capacitance goes down. Say I dump the same charge on. Right, I dump the same charge on. If I increase the plates, the capacitance goes down.
Wouldn't the two plates give them more area too?
We'll get there. Yeah. You got that right. Yeah. Well, next up. Yes.
Your battery's done.
My battery's always about that. You gotta pour coffee. I hear that if you pour coffee on your computer, the battery stays good. Yeah. Thank you. Yes.
But if the two plates in the middle cancel each other out, then technically doesn't the area just stay the same?
Yeah. So you're right. There's an underlying. I'm working off an underlying idea that the area of the two plates is the same. Yeah. For right now. Yeah. For simplicity, spherical count in space. But yes, yeah.
Is there often a time where you'll have like the top plate be smaller in area compared to the bottom plate? Is like that a thing or no?
Yeah, well, I'm trying to give you a heuristic argument for a more general relationship. That's based on not the physical dimensions of the capacitors, but rather how they're arranged in a circuit. So really what I want to say here is that when you have two capacitors in series, it decreases the overall capacitance. Conceptually, you could say it's like increasing the distance between the two plates. Now, I will give you the quantitative relationship to kind of try to answer your question here. Okay? Quantitatively, say, if I want to calculate out a number, okay, you say, well, wait a minute, I got to worry about the area of the plates being different and yada, yada, yada. I don't want you to have to worry about that. So I'll give you the quantitative relationship. Okay? Here it is. When in series, okay, the equivalent capacitance. I'll write it like this: 1 over C equivalent is equal to the sum of the individual capacitors in inverse. Now we could go, I don't think it's a really great use of time I could derive it if we really wanted to. If you, maybe I can type it up, maybe I'll check to see if I have it typed up, but I don't think it's a great use of class time. It's probably better to talk about when Greg puts his foot in his mouth. Right, like what other terrible things has Greg said to his wife absentmindedly? Yes?
Can you give an example of this, because I think I'm just having trouble like visualizing this.
Yeah, let's say the two capacitors are exactly the same. Okay, so let's say that both of them, C1 is equal to C2, and if this helps, let's give them both 10 microfarads. Okay, so we have the two plates in parallel, each of which is 10 microfarad capacitance. If I wanted to replace both of those capacitors with a single capacitor, without changing the overall function, what would that single capacitor have to be? What value would that single capacitor have to be? In other words, I want to replace this with a single capacitor. And the question is, what should the capacitance of that equivalent capacitor be equal to? Survey says
20.
Yeah, and we got to be careful. It's not the sum of the capacitors, it is the sum of the inverse. Yeah, so over here I'd have to do something like 1 over 10 microfarads plus 1 over 10 microfarads equals 1 over the equivalent capacitance. And so, oh good, we're lucky because we have a common denominator, so we can just add the numerators. Right? Be careful there, right? Make sure you gotta have a common denominator before you add stuff. But in this case, we get 2 out of 10. And here's the place where I always forget. Don't forget, it's 1 over the equivalent capacitance. Okay. Sometimes I'll find myself saying, oh, so the equivalent capacitance is 1/5. Like I forget that there's an inverse in there. I forget that this is 1 over. So if I want to get the equivalent capacitance, I have to flip both of the fractions, and so I get that the equivalent capacitance is 5, and this would be in microfarads. So conceptually, what happens is that you essentially double the distance between the capacitor plates. And if you double the distance between the capacitor plates, it should have the capacitance. Let me write that up. Parallel plate capacitor, C equals epsilon naught the area over D. If I double the distance between the plates, it halves the capacitance. So this relationship I've given you here, that all boils down to the fact that the capacitance depends on 1 over D. And that's perfectly extendable. So I gave it for 2 capacitors. What happens if you have 10 capacitors in series? Just add all 10 in inverse and then take the inverse of it, or 50, or 1,000. But that's why, so there was concern about, well, how do you know the 2 capacitors have the same area? This is a little bit more general. It does it in terms of the overall capacitance. So then you don't have to worry about the geometric details. Is it? Okay, yeah. Yay, nay? Yes.
So basically, all the plates in between, if you have capacitors in series, the only two that matter are the ends.
Yeah. In terms of kind of conceptualization of what's going on, yes, the only two that matter is the top plate and the bottom plate, and the ones in between all quote unquote cancel out. Yeah, conceptually speaking, yeah. Yeah, that's the idea at least. Yeah, I'm just trying to give you some sort of way to latch on to, yeah, what's going on there. Yeah.
So what's the point of having a series then?
Why would you have them in series? The potential drop. Okay, so if the two capacitors are the same, okay, yeah. The potential drop across each capacitor could be different. So each capacitor will have the same charge, right? But if each capacitor has a different value, then the change in potential across the capacitors will be different. Yay, nay? If I may, I'll, at the risk of relying too much on the equation, we say, hey, these two capacitors have the exact same charge on their upper and lower plates. Let's say that they're different capacitances. So instead of 10 microfarads each, let's make one 20, and I'll make the other one 10. Okay, just to give us a different value to work with. Okay. Now, the capacitance is defined as the change in potential of the capacitor divided by the capacitor's charge. So which capacitor is going to have a larger potential drop across it? The 20 microfarad capacitor or the 10 microfarad capacitor?
Can you restart?
Yeah, oh.
Back to the equation right there. And
I'm sorry?
so when you did the epsilon naught and the A over D all over the capacitance equal delta V over T, I kind of lost me there.
Where'd my cursor go? Wake up. Where'd it go? Is it flying up? Okay. Oh, no, okay, there it is. Let's go this way. And it goes off screen and it should appear here. Okay, there we go. Un momento. There. Let me restart with a new slide now. Okay. So this, let me change this. Put this back to 10, and I'm going to erase this. New question. So, wipe your brains of the past problem, new question. We'll again consider two capacitors in series. So I'll call this one capacitor 1, and I'll give it a value of 20 microfarads. And capacitor 2, and I'll give this a value of 10 microfarads. And I'm going to go ahead and charge it up. I'm going to connect it to some battery to make sure that there's some positive charge on the upper plates and there are negative charges on the lower plates. Now, we've already argued that the charges on each of the capacitors are the same. Right? Charge that leaves the top capacitor gets forced onto the bottom capacitor. Okay? So if I want, we could say that the charge on the top capacitor, what I'll call Q1, is equal to the charge on the bottom capacitor. the question I would like to ask is, how does the potential drop across the first capacitor compare to the potential drop across the second? So how does the potential drop across the first capacitor compare to the potential drop across the second? If they both have the same charge, which they should because they're in series.
Now, when you say drop, you just mean how do they change?
Yeah, so if I look at the potential of the top plate and compare it to the potential of the bottom plate, I get some difference. What say you? The top capacitor has a larger drop. I agree. How much of a larger drop? Yeah. And this is where, okay, now I'll write in the equation again. I erased it, but I'll write it in again. The drop across the capacitor is given by the charge of the capacitor times the capacitance. I've just taken the definition of capacitance and I've moved around the Q. Okay. So originally when I gave it to you, I said, let's see, delta V over Q is equal to C. Now I'm just rewriting it. The drop across the capacitor is the charge on the plate times the capacitance. So if I have twice the capacitance and I have the same charge, I should have twice the potential drop. And I'll go ahead and put it in here. Said V1 is equal to the charge on capacitor 1 times the capacitance. And I'll Q the charge on capacitor 2 times the capacitance. And then I say, oh, goody, goody. The charge on the first capacitor is the same as that on the second because they're in series. So I can cancel. And so I discover that the drop across the first capacitor as compared to the second is simply the ratio of the two capacitances. And 20 divided by 10. So he said, why would you ever want to put capacitors in series? One reason is if you need to control the potential drop across them. So for example, say for some reason you want another wire in here. You can now control what that wire, the potential that wire's at. For example, by tuning which capacitors you have. So for example, if you want, oh, okay, yeah, I'll leave it there. Say, if this battery, let's say I hook it up to a 3-volt supply. Sorry, that's terrible. The drop across the top capacitor will be 2 volts and the drop across the bottom one will be 1. And so this wire now is at 1 volt. Has a potential of 1 volt above the bottom plate. Above. Or say you need it to be at 1.5 volts, you'll put 2 capacitors in that are exactly the same, and it'll cut the potential in half. Now, let's see here. Oh, okay, we're out of time. That's at least theoretically one thing you could do. There's more practical applications, but we'll start there. Yeah. So, yeah, hey, thanks for your attention. Monday, we'll take care of the capacitors in parallel. And you probably already have an idea that if I put them in series, that's like increasing the distance. What happens if I put them in parallel? What that means is that charge has an option of going one route or the other route. Okay? So go ahead, think about how that would change the capacitance, and I'll see you Monday. Sorry, all of the great funny stories are done. Back to business.